What's up? Welcome back. In this episode, you'll learn how to solve day 18 for the advent of code in 2023. This one's called Lava Duct Lagoon, and our goal is to sort of like dig out a path for a big lagoon where the lava can flow and stay for our machine parts factory. We are given some instructions in the beginning, which is like a dig plan or a plan for how we want to dig. And they are given to us in this sort of breakdown where we have the direction we're going to go, whether it's right, left, up, or down, how many steps we should take in that direction, and then the color that we should paint the wall in hexadecimal. And after we go through the instructions above, we would end up with a trench that we've dug with the trenches shown on the grid with the pound sign, and then the space in between is shown with dots. And that would end up digging this trench. And inside of it is where we're going to put all the lava. And so here, if we were to go through and fill in the trench completely, we would end up with 62 cubic meters of space inside of the area here, inside of the trench. A couple problems ago on Advent of Code, we used the point in polygon algorithm. In that same problem, there was a bunch of solutions on Reddit that talked about the Shoelace Formula and Pick's Theorem, which are two different approaches to figuring out how many dots are inside of a polygon. And so what we're going to do is start off by drawing the walls here, and then we'll use the shoelace formula to figure out what the area is, and then we'll use Pick's theorem to calculate exactly how many dots are inside of our lava thing. And we might also get into some optimizations here with Enumerator. Let's grab the example input though, just to get started, and we'll drop that in like always. So we're going to put this in here and then input. Okay, and we want to pull off these instructions. So we'll say input.split on new line dot each do line. And so for each line, we're going to have, maybe I think we can just split on space, and we'll get like the direction, the steps, and the color. And we want to convert this direction, left, up, or down, into directions that we can travel within a grid. So we'll say maybe like dir is this thing, or dirs, and we're going to have right points at something. We're going to stay in the same row. We're going to increase the column. Left, up, down. This is actually backwards. Up will be -1, down will be 1. Okay, so then what we want to return from this is we want to convert steps into its integer value, and we want to convert dir into its direction value. And in this first part of the exercise, we don't actually use the color. It says that we're going to paint it with that color, but the color isn't used. We will return the direction and the steps. And maybe we just map over this, and this will give us back some instructions. Okay, so now we want to like p instructions just to see what they look like. And we'll run this, and we get back 0, 1. So that would mean we're going to the right, and 6. And that's how many steps we should go. Okay, so let's go through each of these instructions and draw them out on a grid just for fun. We're going to have like our map or like positions or something, or let's call it a wall. And the wall is going to start with some like current, and that will be 0, 0. Let's just say we're going to start at some arbitrary position 0, 0. And then what we want to do is we'll start out with our wall having current. And for each of the instructions, we're going to update current. So for, the step number of times we want to do something, steps.times do. So every time we take a step, we want to update current to be the direction. Yes, we're going to increase the first element by the direction and the second element by the direction. And then we're going to add that into our wall. And at the end, we should p wall, and we should have something here that, something that looks interesting. We want to find like the minimum and the maximum heights of the wall. So we can do like wall.map.minmax. And we'll also do the same thing for the last. Just because we want to visualize this, right? So we're going to get min row, max row is equal to this. Min call max call is equal to this. And then we want to go from min row to dot each, do that, max row dot each, do that. And then if the wall includes that, we'll print out a pound sign. Otherwise, we'll put out a dot. Okay, this looks like the correct sort of grid. So that's awesome. So we know that at least our wall is probably being drawn correctly. Now we want to implement this shoelace formula. So the shoelace formula says that the area of the polygon is equal to going through and summing up the absolute value of the x value. So we have like x1. We're going to take x1 here. This image is the best. So we're going to take x1 and multiply it by x2. And then we're going to take y. We want to subtract that from y1 multiplied by x2. So we want to kind of like take the opposites here. So we want to go through each consecutive 2. So we want to go through each of the pairs of the dots that are within the wall. And we're going to get some x1, y1, and x2, y2. And for each of those, we want to multiply x1 times y2. So we're going to do x1 times y2. And we want to subtract that from y1 times x2. So minus x2 times y1. So you're like, the reason it's called the shoelace theorem is that you're like crossing, multiplying the cross of the two. And this is going to give you from that you want to take the sum. We're going to sum up all those differences and we'll take the absolute value of the whole thing. Or maybe I think we might want to take the absolute, Okay, so each cons of 2, because this isn't going to map. We'll just do like dot sum of that and then dot absolute value. And then from the absolute value, now we want to divide the entire thing by 2, and that should give us the area. fdiv 2, and this should give us area. So if we p puts area, let's take a look and see what we get. So we get 42. So 42 is the area that it's telling us. So it expects that inside of here, there is an area of 42. So that is the first part of the problem. Now what we need to do is use Pick's theorem here in this other formula, and using our boundary points, we need to kind of like subtract out the bits that we've already got on the boundary to figure out what the interior is, and then we can add the interior to the boundary points. So we have wall.length. This is going to be our b, I think. If we run this, we get 39, and we want to divide that by 2, or this is like our b over 2. The Pick's theorem thing says that area is equal to the number of interior points plus b over 2 minus 1. So let's just get that working. Now, okay, so now we can say that our interior points is like a minus b over 2 plus 1 or something. So we should get, let's print out our area minus the wall length over 2 plus 1. And what do we get? We get the number 24. So that should be our number of interior points is equal to this thing. And then we want to say puts interior points plus wall dot length to add the border like back in. And that should give us how deep our is. So we get 63. And in the example input here, it was expecting 62. So we are off by 1 somewhere, and we might be able to just, that plus 1. I actually think wall length. The wall length might actually be 1 extra since we added in the current position without moving. Let's see. So maybe we want this still plus 1 without 0, 0. Okay. Now let's try it against our puzzle input. Okay, so we're going to grab our puzzle input, drop it here at the bottom, and then change our input to be input is data.read, and let's see what we get. Okay, we got some giant output. Let's run it over here. Sweet. That's pretty cool. So it's drawing this giant space where our lava is going to go. But that's taking quite a while. So we actually don't need to do this printing out stuff right now. So I'm going to comment that out and we'll just run this. Okay, so we're printing out two different numbers. What are we printing out? Oh, we're printing the area and then our answer here, 48503. So let's come back over here. And our puzzle answer for part 1 was 48503. Okay. It was a little bit cool to see the actual puzzle output. All right, so this is pretty neat. This is going to be the space, like we're drawing the wall around where the lava is going to be stored in this giant lava lagoon. Really interesting to see as the wall is like being drawn out here. Very fun little project here. Okay, so we're zoomed way out, but this is what our lagoon would actually look like. That's fun. Oh, hey, real quick, a shameless plug, buildandlearn.dev. This is a podcast where me and my buddy Colin hang out and we talk about software development and also just things that we're building and we're learning. So if that kind of stuff interests you, head over to buildandlearn.dev. You can listen on any of the podcast players that you're used to. So yeah, let's get back into Advent Code. Cheers. Let's go take a look at part 2. The elves were right to be concerned. The planned lagoon would be way too small. Okay, so after a few minutes, someone realizes what happened. Someone swapped the color and instruction parameters. So each of these hex codes is 6 hex digits long, and the first 5 encode the distance in meters that we're going to take steps as a 5-digit hex number. And then the last hex digit encodes the direction. 0 means R, 1 means down, 2 means left. Oh my gosh. Okay, so now what we got to do is look at the color. It's all about the color. None of it is about the steps or the R left and D. So now it's all about looking at this number here. So yeah, so we've got to, maybe we need to modify our instructions here so that the dir is actually some other direction. So maybe we'll say dir's, oh, actually, yeah. Before we even get there, let's break up our color. So our color now has all of the info, right? So we want to take, maybe we have, color is equal to color dot gsub, all of those bits. We want to take off the parens and the pound sign. And then let's also grab off. So the first 5 characters are the steps and the last character is going to be our direction. So now we can do color from 0 up to 5 is going to be our steps. And a hex number, if we take any hex number, we can convert that into a decimal or to an integer in Ruby. So let's take a look here real quick. We can say if a is the value 1 and we say a.2i, we know that gives us back a 1. But we can also pass an argument into 2i, which will be the base. So in this case, we get back 1. But what if we made a the letter A, and then we convert it to an integer from the hexadecimal value? We get back 10, right? Because when we're counting in hex, we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. F is 15. Oh my gosh. Okay, yeah, because FF is, that's part of the color scheme or whatever. So if we got these first 5 hexadecimal values, and we said A is equal to this, then its actual integer value would be this 461937. And if we go look back here, 461937. So we should be going to the right and 461937 steps. That's a lot of steps, right? So here we can do 2i of 16. So that's going to be our steps. And then our new direction is going to be, we need some new mapping between our durs. So let's copy this for a sec and make a comment here. And we're going to change this to 0, 1, 2, and 3. Okay, and we'll rename this to durs 2 or something. So now we should have new directions and some new number of steps. Okay, and before we get down here to the wall or anything, let's comment that out. And we'll just p_wall.length. And let's take a look and see what happens. Ruby main.rb. Okay, dir, something about this isn't actually, oh, oh, this needs to be color at 5, I think. Okay, it's hanging. Now it's hanging because as we're iterating through all these different steps, now our number of steps is going to be massive, right? It's up to, what is that? 16 to the 5, 16 to the 5. So our steps might be up to like in the millions, right? We're going to go up to the millions in one direction. So instead of just adding current directly into wall here, I think we might want to take a different approach, that instead of building up an array and then iterating over the array, we want to instead use some sort of generator or enumerator. So we'll look at that next. Okay, yeah, so our array is 195 million elements long, our wall array. And it took 1 minute, 11 seconds just to build the array, because I'm sure it's using tons and tons of memory. In order to make this run fast enough to work against our massive example here, we don't want to build up an array of points on our wall. Instead, we want to carefully iterate over each of the instructions and the steps, and we can yield those pairs to our counter here, so that instead of building like this massive array, we can just like work through and stream maybe our instructions. So in Ruby, there's a class called Enumerator, and this Enumerator class is purely for going through internal and external iteration. Maybe you've created an array with a bunch of stuff in it before, and if you call .each on it, a.each here, we get back this thing that's called an enumerator. And this enumerator, again, is purely for knowing how to iterate over stuff. So if we say that x is equal to a.each, one of the methods on x is next, and this is what is used to get the next element as you're iterating. So we can say x.next again. That'll give us 2, then 3, then 4, and then finally, if we run out of elements that we can iterate through, the way that the enumerator object works is it raises this exception that is of type stop iteration. So that's how you can handle the end of the line or whatever. But what we want to do is create our own custom enumerator so that we can yield individual instructions as we're like working in a certain direction. So let's make a new method here called defgen, and this is going to take in some instructions. And we're basically going to rewrite this section of code here, but instead of creating an array, we will yield each element. So we still need the concept of current, and we're still going to do iteration, but instead of building up an in-memory array of wall here, we're going to create enumerator.new, and that's what we're going to return, is this enumerator. Now, instead of using the push method to add to an array, we're going to use this push method on the enumerator itself. And that's sort of like yielding to the enumerator. So this is how we give it the next element that we want it to look at. Here, by calling gen on some list of instructions. In fact, if we just copy this and paste it into IRB here, and we say gen with the instructions, I guess this is going to take it, it'll get a direction and the number of steps. So if we tell it to go to the right, that's our direction, and we want it to go, I don't know, 10 steps. If this is our instruction here, or our list of instructions, that's going to give us back an enumerator. And if we grab that enumerator by a name, so let's slap a label on it, we'll call it en is equal to that enumerator. So if we say en.next, that gives us the next element in the iteration, en.next, 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 until we get through the list of all of the instructions. Pretty handy. And that will enumerate all of the different pieces of the wall for us. Let's actually just comment this out. This is like the array implementation, and then we'll use a generator implementation. So here what we want to do is, instead of iterating over the wall, we want to iterate over the generated instructions. So we're going to call gen and pass in instructions. And then we want to go over each consecutive result from those instructions. And we want to do this shoelace algorithm on that, get out the absolute value, divide by 2, and that should give us back the area. So if we run this against part 1 code, just so we can verify that it's doing the same exact thing as before, we can run ruby main.rb. And now we're running into an issue where it's saying, oh, we needed the wall length in order to calculate our interior points here. So in order to know like how long the wall is, we need to count up the instructions here. There might be a way to do like .width index to figure out how far we go. But another cool thing that we can do is pass in a counter. And this could be like a lambda that is executed as we go. So we're going to pass that in to our generator here. So we can keep up a wall length and then pass a lambda that is a callable in here that will execute wall length plus equals 1. And at the end, we should get some wall length that we can use here instead of the length of the array. And that's looking pretty good. 42 or 62 is the answer for the example input for part 1. So let's run it against part 2 and see what we get. Okay, 1 second. It's running in 1 second against part 2, and that looks correct okay, so that is the example input for part 2. So now if we run it against our actual input for part 2, let's see what we get here. While that's running, let me introduce you to memory profiler, this memory profiler gem, which is pretty sweet. You can pass it a block and run your code inside, and then it will give you a very detailed report with all the allocations and a breakdown of the memory usage. So this can be pretty useful if you're trying to figure out like how much memory did this Ruby program actually take. All right, we got some answer. Let's see if that is correct. Boom, that's the puzzle answer for part 2. Awesome. Some ridiculously big number. Yeah, 148 trillion, 442 billion, 153 million. So some ridiculously big number, but we were able to get there in 53 seconds by using this enumerator approach instead of building up all of the arrays. Now, I don't know in practice exactly how much smaller memory is, but I know that, yeah, it at least finishes. That's really what we're looking for here. And it finishes in less than a minute. So not bad, not bad. All right, that's day 18. Thanks so much for watching and for sticking around. We're making our way. We're getting much closer. It's almost Christmas. Yeah, happy advent of code, and we'll see you in the next one. Cheers.